everyone in person, and I don't know if we have anyone attending live today. I'm going to take a quick look. Anyone attending live? Okay, well, we are streaming, and the sound is working. If there is anyone live and you have questions, I will try to check back a couple of times for any questions that might come up online. It's a little bit tricky, but I should be able to see them there if there are questions. So welcome back, everyone. It's good to see you all here again. We still have a few in-person people. It would be difficult giving this lecture to an entirely online audience. So today's going to be something pretty different from the first couple of classes. We're going to take this one class to kind of delve into its own topic, probability and Bayes' rule, before we get back more to hypothesis testing, inference, and other kinds of statistical analysis. So this class is a little bit different from the rest in that we are not talking so much about statistical description or inference here, but really talking about probability and its application to screening tests. And I'm going to introduce some important terminology to you that you will, it certainly won't be the last time you hear it during your programs and your careers, around ideas of sensitivity, specificity, positive predictive value, negative predictive value, in relationship to the prevalence of a disease. And then we'll also talk about some more general things about probability and Bayes' theorem and how that relates to these screening tests. And all of this is covered in the first couple of sections of your textbook in Chapter 2. Let's start out with an example of a screening test, and this is a quiz for you. So pay attention. This is a hypothetical screening test. It's a screening test for cancer, and it is correctly positive for 100% of cancer patients. That is, if you have cancer, it will certainly detect it. Now let's say we apply that to a population where the prevalence of cancer is 5 per 1,000 per year. Then in this population, what is the probability that an individual testing positive has cancer? Maybe I'll ask you something even more general first. If you received this test and got a positive result, would you be worried? Yeah. Everyone would be worried. It's a test for cancer. And it's correctly positive for 100% of cancer patients. But let's get more specific. So you're part of this general population who is being screened. If you receive that positive test, what is the probability that you actually have cancer? I want to hear some called out answers. So I've given you two pieces of information here. Its accuracy on people who have cancer and the prevalence of cancer in the population. I'll give you a hint that it's a bit of a trick question. Yes? Would be 100%?
That's the test positive is correct. Test positive is correct.
No, it's not 100%. So read carefully again here. It's 100% accurate on people who have cancer, but who's it being applied to here? in the population. It's being applied to 5 people with cancer and 995 without cancer.
What?
Okay.
So what do you know about its performance on those who do not have cancer? Actually, we don't know anything about its performance on those who don't have cancer. I haven't included a key piece of information on this slide. So actually, the trick is that this is unanswerable here. So before you are worried about receiving this test, that would be a good piece of information to have. What is its positive predictive value? That is what this last question is asking. And that is the thing that really matters when you receive this test, not this accuracy on people who have cancer. And that's a really important distinction. And I think one that has caused a lot of anxiety among people receiving screening tests, and also caused a number of problems for screening tests as they move from a case control setting where, say, 50% of people have cancer to a population where a much smaller percentage have the disease being tested for. And I'll talk more about why. But to give you an extreme example of how you don't know whether you should be worried or not here, let's say that this test simply says positive to everyone. It's just like a piece of paper that says yes. Right? Then that meets that first criterion. It's correctly positive for 100% of cancer patients, but it's wrong for everyone who doesn't have cancer. So you need both of those pieces of information to know to answer this final question. So the key thing there is that, yeah, for every 1,000 people you test, it's being applied to 9,995 healthy people. And so we need to know something about its performance on the rest of that population. Does that make sense? A priori, before you go in and have that test, you have a 99.95% of not having cancer. So it needs to be a pretty strong piece of evidence to say otherwise. It needs to be pretty accurate on that negative population in order to take that to being a 0% chance that you don't have cancer. Excellent. So in an ideal world, screening tests would be 100% accurate, and then you could just know when you got that test back whether you had cancer or not. But in reality, most, not all tests make mistakes. And they make mistakes in 2 ways. There are the false positives, where it tells you you are positive for a disease, but it's wrong. You don't have it. Or the false negative, where it gives you a negative test for a disease that you actually do have. And this is a key thing to remember here, that the performance of a test depends both on the properties of that test and on the prevalence of the disease in the population it is applied to. So it's not just an intrinsic property of the test, it's also a function of the disease prevalence in the population it is applied to. Why is that? Yeah?
Make sure that it's testing what is, or producing results what is actually testing or what is measuring. Right? Just with specificity is there, or is it
so specificity and sensitivity, and I'll talk more about these, but those are actually intrinsic properties of the test. But those positive predictive value and negative predictive value are properties both of the test and the population that it's applied to. And the reason is because its performance in a population depends both on its false positive rate and its false negative rate, or its sensitivity and its or its specificity and its sensitivity. And one of those applies to the people who do have the disease, and the other applies to those who don't have the disease. So in order to know that overall performance, you have to know that proportion who do and do not have the disease. And how do we know that sort of truth about whether or not someone has a disease? Well, we're going to compare it to a so-called gold standard, which is some other very accurate but more expensive or invasive test. So whereas the screening test might just be a simple blood test, gold standard might be an actual invasive examination, and one that involves inspection by a pathologist or some other thing that cannot be done on as large a scale, but is more accurate. So in the case of some things like, is it that the NFL players get chronic traumatic encephalopathy? The gold standard there can only be done posthumously after death. So in general, it's something that is not practical to do for everyone, but it's the only way to actually get the truth and to compare the screening test to. Yes?
Like with HIV, you did the rapid test, right?
Right.
And then you always have to go for confirmatory.
Yeah, so that is an example. With HIV test, there's a rapid test, which is fast, convenient, but it's not the gold standard for accuracy. The gold standard for accuracy takes longer, it costs more. Yeah.
Will the gold standard have false positives or false negatives?
We have to assume that the gold standard is correct. No false positives, no false negatives. You know, that's debatable in some cases. The gold standard could be wrong sometimes, but we have no way to know. It's the best information that we have. But good question. Okay, second example. I'm going to start putting some more realistic numbers in here. So in this example, we have a test for chlamydia infection that is being applied in two different settings. The first setting is a sexually transmitted disease clinic where the prevalence of chlamydia is 30%, because the patients who go in there are going to get tested because they believe they are at risk of having received an infection, or they have symptoms. And the second setting is a private practice where this is being done as a precautionary screening, but not because the patients have gone in for the purpose of STI or STD screening. So in the first, the prevalence is 30%. In the second, the prevalence is 3%. And I'm taking this from an article that I've posted with this week's notes that I would recommend taking a look at. It's a very nice article on the uses and abuses of positive and negative predictive value. So we have, let's see, this rapid screening PCR test, polymerase chain reaction. This is our screening test. And then we have our gold standard, something else, which tells us whether someone really does or does not have the chlamydia infection. So let's see, our PCR test. So on the it's giving us overall 315 positives, 685 negatives. In our gold standard, we know that we have 300 positives and 700 negatives. So first thing, let's calculate here is the so-called positive predictive value. So that is the probability, given a positive screening test, that you really have the thing that it is testing for. So here, this column is those who received a positive test for the screen. And from the gold standard, we know that 294 out of the 315 really have chlamydia. From that, we calculate positive predictive value. It's 294 divided by 315, which works out to 0.93. And the negative predictive value, that is the chance if you receive a negative test that you really are negative. So here are all the people who received a negative test, and out of them, 679 out of 685, or about 99%, are really negative. Now, this is the same test being applied in this different population. If we calculate, for example, the sensitivity, which is the probability of identifying positive cases, the thing that was 100% in that cancer example, it's 294 out of 300 and 29 out of 30. The sensitivity is the same, and the specificity, that is the accuracy on the negative cases, or the probability of predicting negative if someone is negative, is 679 out of 700, and here 971 or 941 out of 970. So going to this other population where the difference is that the number of positives and negatives are different, our negative predictive value has gone up to something pretty close to 100%, and our positive predictive value, that is, for those who received a positive test, actually only half of them have chlamydia. So that's gone down to 50%. So this is the thing that I was asking you about on the first test. If you received a positive test, what is the probability that you really have the disease? And the key thing here is that it depends on the prevalence of the disease, not only the properties of the test. So to put this another way, positive predictive value and negative predictive value, those are probabilities conditional on what you got on the test. So it's the probability of having the disease conditional on having gotten a positive test, or not having the disease conditional on having not gotten having gotten a negative test. Whereas sensitivity and specificity are conditional on the gold standard, whether or not you have the disease. So they don't depend on the population, because they're the accuracy on people who we know have the disease or we know don't have the disease. Any questions?
Thank you. So one more time.
Yeah. And I have this written down later too, so that it will come more. But positive predictive value and negative predictive value, these are probabilities conditional on the test result. Whereas sensitivity and specificity, these are probabilities conditional on the gold standard. So sensitivity is the accuracy on positive cases, and specificity is the accuracy on negative cases. those are intrinsic properties of the test that have nothing to do with the population it is applied to, or they have nothing to do with the prevalence because it's applied to people where we know whether they're positive or negative. Okay, so with those examples, I'm going to go into a little bit of theory now, just starting with some definitions. An event is a measurable definite outcome, such as whether an individual has a chlamydia infection according to the gold standard, whether someone survives past 70 years of age, or an infant survives the first year of life. So these are all measurable and definite. And a probability is the rate of an event for some very large number of observations, such as the probability of getting a chlamydia infection, the probability of surviving past 70 years, or an infant surviving the first year. Intrinsic properties of a test are properties of that test. So it is intrinsic to the test, not to the population that it is applied to. So sensitivity and specificity, these are intrinsic properties of that test. Sensitivity being the probability of a positive test for individuals with disease, that is the accuracy or the percent of correct tests for those who do have the disease. And specificity is that accuracy for those who don't have the disease, the probability of a negative test for individuals without the disease. So does it make sense why I call these intrinsic properties of the test? Because whether you apply it to the private clinic or to the STI clinic, it doesn't matter what the prevalence is because we're separating it out by the individuals who have the disease and who do not. Okay. Let's do another example of type 2 diabetes mellitus. This is highly prevalent in the older population, especially among obese individuals. There is a gold standard test that this oral glucose tolerance test where individuals drink a glucose solution and then blood is drawn at intervals for measurements of the glucose. So you see how the rate at which it is being metabolized by the body. So it takes a while and it's invasive. It requires a number of blood draws. There is, however, a screening test, which is fasting plasma glucose. So you fast for a period of time, you just go in, you get one test, and they measure your amount of glucose in the blood, in the plasma. So here, they don't have that initial measurement. They can't actually measure the rate of decline after your glucose intake. It's just under an assumption that after a period of fasting, it should go below a typical level. So it's easier, faster, more convenient, less expensive, but also less accurate. Yes?
So would the screening will be based on prevalence that you said? Or
no, these are not based on prevalence. the screening test is just, it's a less accurate, easier way to do this assessment. It's positive predictive value and negative predictive value. Those will depend on prevalence for sure.
Still trying to understand prevalence.
I have more examples. So this is from a nice set of slides from Johns Hopkins School of Public Health that I found. So we go through some demonstrations of what happens with this screening test. So on the y-axis, we're looking at blood sugar from low to high among diabetics and non-diabetics. So we've got 20 diabetics and 20 non-diabetics. And this is a demonstration of how among the diabetics, it's on average higher than among non-diabetics, but there's a fair bit of that overlap. So it's not going to be a perfect test. So you can set a threshold somewhere. You could set it low. So this is going to be a sensitive test. Sorry, this will be a fairly specific test in that anyone with a plasma glucose level below this is going to be called diabetic. Sorry, do I have this? I've got myself confused here. Help me out. What's that? Yeah, everyone above this threshold is going to be called diabetic. So out of the true diabetics, the test is going to call 17 diabetic and 3 non-diabetic. Among the non-diabetics, it's going to call these 14 diabetic and these 6 non-diabetic. So this is a fairly sensitive test because it has caught most of the diabetics, but it's not a very specific test because a lot of the people without diabetes have been called diabetic. 14 out of the 20 non-diabetics have been given a positive test.
That's false.
These are the false positives. Yeah. Yeah, we actually have a 14 out of 20, a 70% false positive rate.
Sorry, can you say that again?
Actually, let me get that right. Out of the positives, I don't want to get into false positive rate quite yet because it'll confuse things more. False positive rate would be out of the positives tests, the fraction that are false positives. We are calling that the positive predictive value. So alternatively, you could set a high threshold, and by changing this threshold to something higher, we've lost a lot of sensitivity because we're now only calling 5 out of the 20 diabetics as diabetic, but we've improved on our specificity. So the sensitivity is the accuracy on the positive cases, which is down to 25%, and the specificity is the accuracy on the negative cases, which is now up to 90%. So this choice of thresholds, this is part of the intrinsic property of the test. So the things that are going to affect these intrinsic properties are how much overlap we have between test values among the positive and negative cases and where we set that threshold. And however we set this threshold, there's going to be some trade-off between sensitivity and specificity. That's a pretty fundamental attribute of diagnostic tests and all kinds of measurements, that you have a trade-off between sensitivity and specificity. In general, for one given technology, if you improve one, it comes at the expense of the other. You can only improve both of them with a new, some fundamentally different approach to the measurement. Now, in a typical population, there's no line separating these groups, and the subjects are mixed. And in fact, we don't know who the diabetics and the non-diabetics are. So when you set this threshold and call this, so in that previous example, we have the gold standard applied to all of them. This is something that you would do when you're testing the test and proving its efficacy. But then when you go apply it to the population, this is all you have. You know, for a given threshold, how many you are calling diabetic and how many you're calling non-diabetic. And all we know is that for that high threshold, we called a few people diabetic. At the low threshold, we called a lot of people diabetic. So this is a basic trade-off that developers of diagnostic tests have to make. And they're going to make it somehow based on the relative costs of false negatives and false positives. So, conclusions about sensitivity and specificity, different cut points, the different sensitivities and specificities. That cut point determines how many subjects will be given a positive test. You set that threshold low enough, you will give a positive test to everyone, like in that first little example that we gave. And there's this trade-off. Any cut point that identifies more true negatives will also identify more false negatives. And conversely, a cut point that identifies more true positives will also identify more false positives. We're calling that sensitivity and specificity. These are called intrinsic properties of the test. PPV, positive predictive value, and NPV, negative predictive value. These are properties of the test applied in the population. The positive predictive value is the probability that someone with a positive test does in fact have the disease, and the negative predictive value is the probability that someone with a negative test does not have the disease. So these are the things that really matter to the patient and the physician. It's not so much the intrinsic properties of the test, they want to know what the test means to them. So going back to this example with the high threshold, we had a positive predictive value. So among people receiving the top positive test, positive predictive value of 5 out of 7, negative predictive value of 18 out of 33. I lost my slide here in the other instance, but if we were to move the threshold back down here, Then among those receiving a positive test, their PPV would be getting down closer to 50%, and the negative predictive value would be getting better. So essentially, by calling fewer people positive, you get a better positive predictive value. By calling fewer people negative, you get a better negative predictive value. Because we're getting into the zone where we can be more confident about those positives, or down here about those negatives. And this really matters, and I think there is a lack of understanding about the importance of positive predictive value when applying a new test to the population. And there have been real cases where a test that was accurate in one population was then applied to a broader population with a much lower prevalence of the disease, resulting in a low positive predictive value and a lot of false positives. So some of the well-known cases about the positive predictive value of tests are mammographies for breast cancer, prostate cancer screening, and this one that I thought was really unusual. This teen screen, something that was supposed to screen teenagers for current or future mental health problems. And I'll just emphasize that when you take any screening test and apply it to a population with a very low prevalence, so you start, giving mammographies to women under 40, prostate cancer screening to men under 40, where the prevalence of these diseases is very low, you have to have an extremely, extremely accurate test on negative cases in order not to have a lot of false positives. And just because the test performed well on higher risk populations does not mean that it's going to have that same performance than going to lower risk populations. I will introduce some probability to you and then introduce Bayes' rule to you, which will allow you to actually convert between these different probabilities between sensitivity, specificity, and EPV and PV. So, you remember what an event was? That was the specific measurable outcome. If A and B are two different events, then A, this U is the union of A or B, A or B. So that's having one or the other of those events occur. The upside down U is the intersection of A and B. That means both of these events happen. A superscript C I will use for complement, meaning that A did not happen. Noting that the probability of event A plus the probability of its complement is always 1, because an event must either happen or not happen. And this is an important one. The probability of A conditional on B, this is the probability of A happening conditionally on B being true, or B having happened. Conditional probability. So everything I've been talking about so far has been conditional probability, like the probability of having the disease conditional on having received a positive test, conditional of a positive, or the probability of a positive test conditional on having the disease. I just wasn't using the word conditional, but those are conditional probabilities. We can draw Venn diagrams. These are Venn diagrams to represent these intersections and unions. So in a Venn diagram, this circle represents A having happened, and this other circle represents B having happened. And so this bit in the middle is A intersection with B. So this idea of A and B occurring is shown graphically in the form of overlap between these two circles. And what these circles are really representing here is a probability. We use them for probabilities to say if this area represents the probability of event A, and this area represents the probability of event B, then this bit in the middle represents the probability of A and B because it's inside both of those circles. And the total area between the two circles is A union with B. So it's the probability of either A or B or both happening. And we can make even larger Venn diagrams. 3 is pretty easy. It starts getting kind of hairy as you get to 4 or more. People do draw Venn diagrams with more than 4 events, but we can extend things like the intersection and the union to multiple events. That is more than 2 with the bit in between all of them being A intersection with B intersection with C, or A and B and C. Okay, I have another little quiz for you, easier than the first one maybe. What would you call this? So you're interpreting these Venn diagrams. I wonder if I can draw here. What is this? This is the probability of what? B. Very good. Okay, how about this one?
A union B.
A union B, very good. A union B. Hard drawing with the mouse. Okay, how about this one? On the D. Very good. Probability of A. Okay, getting trickier now. What's this? A. Probability of. So you're saying this is a conditional probability. Probability of A conditional on B complement.
If
I think it's actually the conditional of A intersection with B complement. The probability of A conditional on B complement would actually be, let me see, the probability of A conditional on B complement. I'm not sure how to represent that in the Venn diagram. Because it would be, well, it would be this area divided by everything outside of B. So it's like there's a normalization in there. I'm not going to do conditionals in the Venn diagram. It's just intersections and unions. What about this one? B and A complement. The probability of A and B. All right, great. Okay, mutually exclusive events look like this. There's no overlap between them, such as being positive for chlamydia by the gold standard and negative for chlamydia. They cannot both be true. It's one or the other. And in this case, the union, the probability of A or B is equal to the sum of these two because there's no overlap. And if these options are exhaustive, such as having chlamydia or not, then that sum of the two probabilities equals 1. Always the sum of all possible events is equal to 1, but in this case, there are only 2. So probability of chlamydia or not chlamydia equals 1. And the intersection, the probability of chlamydia and not chlamydia is 0. So let's take two different events, such as having chlamydia and having heart disease. In this case, these are not necessarily mutually exclusive. There's some overlap here, the probability of having both chlamydia and heart disease. And in this case, the probability of having the union is equal to the sum of the two minus this bit in the middle that we're counting twice, that intersection. And that intersection, the probability of having chlamydia and heart disease, is equal to the product of those two events if they are independent. So if having chlamydia that has no bearing on having heart disease and vice versa, then your probability of having both is just the probability of having one times the probability of having the other. So if you have a 10% prevalence of heart disease and a 10% prevalence of chlamydia, and they are totally independent of each other, then your probability of having both is 0.1 times 0.1, which would be 1%. Okay. Now on to this conditional probability and what this looks like visualized in Venn diagrams. So for these two events, A and B, the probability of A conditional on B is the probability of A and B divided by the probability of B. So for sure, the probability of A conditional on B means that both of them have happened. So A intersection with B, but we have to divide by this probability that B has occurred, because otherwise, you remember in these here the probability of both of them occurring is the product of the two, but in this conditional probability, we know that one of them has occurred. So we have to divide that back out of it. And looking at this in a Venn diagram, it would be this, this intersection area divided by the area of just one of the events, event B. And this formula with the denominator, what goes in that denominator is the given event, the one that is conditional on, the one that we assume has happened. And another way to read this is that of all the times that B occurred, such as heart disease, the probability of A conditional on B is the proportion of those times where B occurred that A also occurred. Does this make sense? Yeah.
So proportion meaning of B, like it's happening inside B.
Right. So if this is if A and B are heart disease and chlamydia, then the proportional of heart disease conditional on chlamydia are the fraction of, or the risk of heart disease among those who have chlamydia. So conditional on having chlamydia, for example. So now we get to Bayes' rule. It's actually, it's a really simple proof. It's just really a property of probability, and it comes from this transitivity of the intersection, that the probability of A and B occurring means exactly the same thing as the probability of B and A occurring. It doesn't matter, like, just like multiplication, 2 times 3 is the same as 3 times 2. So substituting back in this equation we had on the previous page, if I multiply this through by probability of B, then the probability of A and B is the probability of A conditional on B times the probability of B. And because of the transitivity, that has to be the same as if you switch A and B. And that leads to Bayes' rule. And all I have to do is divide through again by probability of B, and we have here Bayes' rule or Bayes' theorem. That tells us what the probability of A conditional on B is, given the probabilities of A and of B and the reverse conditional probability. So it lets us convert between the probability of B conditional on A to the probability of A conditional on B. It's the relationship between these two conditional probabilities. So you can kind of see now how this is going to come in handy for the screening tests, because sensitivity specificity were probabilities conditional on having the disease or not having the disease, whereas PPV and NPV were conditional on getting a positive test or a negative test. So Bayes' rule is going to let us convert between those things. In the language of Bayesian probability, this probability of A conditional on B is called the posterior probability. Probability of A is the prior probability. So, and in this case, the prior probability would also be the prevalence. So that's your probability of having the disease before you've taken the test. And probability of A conditional on B will be your probability of having the disease after taking the test. That's why it's called posterior. And this other conditional probability is called the likelihood, and this probability of B is just a normalizing factor. Okay, so does the probability of A conditional on B equal the probability of B conditional on A? Another quiz for you. My poker face. Give me a thumbs up if you think so, a thumbs down if you don't think so. No, these are not equal. No, these are definitely not equal.
There's some is one.
What's that?
There's some is one.
Sorry?
There's some is one.
There.
Some.
Oh, there's some. No, there's some isn't one either. No. No, the probability of A conditional on B plus the probability of A complement conditional on B would equal to 1 if those are that would equal 1. But no, these don't sum to 1 and they're not equal either. There's a narrow set of instances where they might be equal. But just to give you an example, what's the probability that you would retire given that you have as much money as Trump versus the probability that you would have as much money as Trump given that you retired? They're not the same thing at all, and they're just different things. Okay, more questions for you to make sure that it gets through. Remember this example of the mild, moderate, and severe pain in the treatment and control clinical trial of a pain medication. So what is the probability of being in the treatment group here? Probability that group equals treatment. 0.5, yeah. Probability that pain equals mild. Point 0.2. It's 0.2 because 20 people experienced mild pain out of 100. Remember that both of these are what we called marginal probabilities because the probability of being in the treatment group doesn't depend on your self-reported pain. It's over all of the different self-reported pains, so it can be recorded in the margin, 0.5. And the probability of mild pain is over in this margin right here. It's not conditional on being in the treatment or control group. So now some conditional probabilities. What is the probability that your pain is mild conditional on being in the treatment group? 0.3. Let's see, I don't know the answer yet. So conditional on the treatment group, that's this column only. 15 people out of 50, so 0.3. You're exactly right. 0.3. And finally, how about your probability that you are in the treatment group conditionally on reporting mild pain? Sorry?
Wait, no.
0.75.
0.75, yep. 0.75 because, so it's conditional on mild pain. We're only going to look at this row, and we see that 15 out of 20 reported are in the treatment group. So does this help to kind of make it a little more intuitive what these conditional probabilities are? There are two conditional probabilities of one based on being in the treatment group, one based on reporting mild pain. And these are what we call the marginal probabilities, meaning that they go on the margins and meaning that they're not conditional on anything else. They're just the overall probability of being in the treatment group or reporting mild pain. Yes?
Number 3.
So number 3, the probability of reporting mild pain conditional on being in the treatment group. So for this, I see that the treatment group is in this first column. Yeah, so that's 15 out of 50. Yeah, for number 4, we went this way. We went 15 out of 20. Yeah. So let's apply it to that screening test. We can use it. We can calculate all of these values, the prevalence, the sensitivity, and the specificity. Now in this particular case, we can calculate TPV and NPV directly because we have all of this 4x4 table. But in general, I might not give you the 4x4 table. I might just say you have a test with 98% sensitivity and 97% specificity. What are its PPV and NPV when you apply it to a population with 30% prevalence? What happens to those if you then apply it to a population with 1% prevalence? You can use directly Bayes' rule to calculate these the PPV and the NPV. So so remember the probability of, let's say, cancer given, or sorry, chlamydia given a positive test is equal to the probability of a positive test given chlamydia, that's the sensitivity, times the probability of chlamydia, that's the prevalence, divided by the probability of a positive test. And if you are going to a different population, all you need to know about that population is the prevalence of the disease. And you can recalculate the PPV and the NPV from the sensitivity and the specificity and the prevalence. And you'll get some practice doing that. And you can, of course, the whole point is you can do this without actually applying the screen to the different population and reapplying gold standard and everything. We do it based on its performance in some smaller population, probably in a case control study, where we can get a good estimate of the sensitivity and specificity, and then estimate what its PPV and NPV will be in the population given different prevalence. Actually, I'll just mention here that one really erroneous use of one of the abuses of PPV and NPV that I have seen that does happen is seeing a case control study and then seeing the researchers calculate PPV and NPV in that case control study. It's really a misuse of positive predictive value and negative predictive value, because in a case control study, you can have 50% disease prevalence. You're never going to apply it to a population with that same prevalence of the disease. So it's really pointless and misleading to calculate the positive predictive value in that case control study. It gives a really misleading impression of what its positive predictive value will be in real life when applied to a population with a lower prevalence of the disease. You are welcome to use a Bayes rule calculator. There are some online. You can build one in a spreadsheet. And as long as you know what these different things are, what the probability of true positives is, that is the sensitivity, false positive rate, this is 1 minus the specificity, and in this particular one, the actual probability. This is the prior probability or the prevalence. So I took those sensitivity and 1 minus the specificity from that chlamydia example, and with the high prevalence, got this this positive predictive value, the chance that a positive test means a true positive result of 93%. Then going to the lower population, it goes down to 50%, like we saw. And this is kind of interesting and something to keep in mind, that I can go from 98% to 100% here, this probability of a true positive. This was the example, again, that I gave in the beginning of a test that is accurate on 100% of cancer patients or chlamydia patients. It had almost no effect on the PPV, because in this low prevalence population, it's really the performance on the negative cases that matters, that is the detriment to this positive predictive value. So even though we have perfect sensitivity, it does not mean that we will have a good positive predictive value if you have not good enough performance on the negative tests. So, wrapping up, the probability of having a disease given a positive test does not equal the probability of a positive test given that you have the disease. This first thing is the sensitivity. This is the positive predictive value. The sensitivity and the specificity, these are properties of the test, intrinsic properties of the test, and PPV and NPV are the performance of the test when applied to a population with a given prevalence of the thing being tested for. And those are related by Bayes' rule. You'll get practice. You should be able to go back and forth to calculate either any of these from the others. They're not the same thing, but they're related by Bayes' rule. A little wrap up of the notation, and that's all I have for lecture. Any questions before we take a little break? Oh, let me check online. I haven't. Oh, there were some questions. So will you be talking more about complement, Tony?
What's that?
Complement?
Complements meaning the Venn diagrams?
Yeah,
I could.
okay. Oh, it was answered. Thank you, Daniel.
Oh, okay.
I should have you next time bring up the YouTube page in the background so that you can tell me if there are questions. Otherwise, it's
Oh, yeah, I hadn't thought of that.
yeah, I couldn't see that there were questions as they were going by. Would the gold standard be different for the two populations? No, I think the gold standard test is just gold standard test. It's not dependent on the population. And yeah, I hope the complement will become clear, I think, in it as we go on. Any other questions before I wrap up the lecture? Very great.